Continuing section 8, another conceptual question to kind of try and build your feeling for the concept of torque. So you've got 4 different pictures of somebody holding a meter stick. So its length is 1 meter, but you're holding it in different positions. The weight that's suspended from the stick is sometimes in different places, and you're supposed to, when it says rank the difficulty of holding the stick, that's the same as saying rank the size of the torque. The more torque you have to exert, the more difficult it would seem to you. So pause it, figure it out, and now we'll unpause it and I'll explain this. Maybe first of all, I'll just give out the answer and then go over the details. It goes BACD. For some parts of this, you don't need exact numbers to see what the answer, or at least I don't need exact numbers to see what the answer is. But if you so in situation B, you have a force equal to the weight of this box. We're assuming the stick itself, maybe I should have said that before you got into this. We're assuming the stick itself is lightweight enough that you can ignore it. Okay, it says that right in the question. Weight is negligible. So you've got this box hanging on the end, and in this case, its weight acts a distance L from your hand. So the torque is going to be L, the length of the meters. Well, L is 1 meter if it's a meter stick, but just to be kind of general about it, for anything like this, it would be its length times the force. Force times moment arm equals torque. Newtons times meters gives you the torque in Newton meters. Now in situation A, I guess I was doing it like that. Now you're holding it at an angle, pivoted there where you've got hold of it. The weight is still hanging from the tip of the stick, but this is L. The moment arm is L. This is supposed to be 30 degrees. Moment arm is L cosine 30, or L sine of 60, if you'd rather look at it that way. So, like I said a moment ago, you don't really need to get into the exact numbers. If this was 25 degrees or 41 degrees or anything else, it would still be the same story. With it tipped, the moment arm is going to be shorter than it is with it horizontal. So A is less than B without really needing to get into exact numbers. But if you want the exact numbers, it's going to be .866 times L times mg. So here, I mean, the force is going to be the weight in all 4 cases. Okay, we're just looking at the difference in the moment arms. This factor will not change between A, B, C, and D. So you've got the full length L Here you've got 0.866 times L. Then when you get to part C, well, the moment arm is labeled right on the picture. Thing is kind of tipped downward like this. Upward or downward doesn't really make any difference. The moment arm is still shorter than if it was horizontal. So this time the weight has been moved back up the stick instead of being right at the tip of it. And there's the force's line of action. I should have maybe left a little more space to write, but it says this, well, I guess it labeled it down here on the picture that came with the question, but that doesn't make any difference. From the pivot point to the force's line of action is, if this is 1 meter long, this would be 75 centimeters. Okay, so mg times L, mg times 0.866 L, mg times 0.75 L, and then for the last one, you've got it tipped the same way again. But the weight has been relocated along the stick once again, so that this time it's from here to here. It's 0.75 L. Your hand is up here. That's effectively the pivot point. Well, you know, we don't even need an exact number, okay? You've got a right triangle here. The hypotenuse is the longest side of a right triangle, so if that's 0.75 L, this is less than 0.75 L. The exact number doesn't matter. All that matters is that that's going to be less than this, which was less than all the others. So I guess I should have labeled that. This is D. So listed in order from greatest to least effort needed to hold the stick, B, A, C, D. And then at the very, I'm not even going to bother to move the camera, but at the very bottom of the page, it says 2 conditions for static equilibrium. Static equilibrium, once again, as far as what the terminology means, static equilibrium is when you have an object at rest remaining at rest, such as a piece of some kind of a structure would be in static equilibrium. We looked at some problems that fell under this heading several weeks ago, back in the unit on F equals MA. I said, if you've got a piece of some kind of structure, a building, a bridge, whatever, then if it's just going to sit there in the same spot for year after year, its acceleration is 0, and that makes the sum of the forces equal 0, okay? In general, sum of the forces equals MA, but if A equals 0, then the sum of the forces equals 0. Well, and there was a problem in the homework where there was a box hanging from some ropes, and you had to figure out the tension in the ropes. Having a net force of 0 is a necessary but not a sufficient condition for an object to remain at rest, okay? For example, if I had, well, let me just draw a sketch up here. If there was a table sitting over here on the floor. And this is looking down from above, okay? You're kind of leaning over the table, looking down at it. So if somebody was to, if I had two students come up to the front of the room, like I've got any students in this room, and I told one of them to push on this table with a force of, I don't know, 20 pounds on that corner. And I told the other student to push on this corner with a force of 20 pounds. Well, I've got, if I'm standing here looking at the table, I've got 20 pounds that direction, 20 pounds in the other direction. That's a total force of 0. And so the first condition of equilibrium, sum of the forces equals 0, has been met. And because of that, the table's not going to go anywhere. It'll just stay right there, but it will not remain at rest. As you can probably see from this, it's going to start to rotate, okay? Because even though you've got no net force, the combined effect of these forces is going to create a torque. And so for something to remain at rest, you have to have both translational and rotational equilibrium. And I'm going to, well, I can get rid of my picture. I'll just put it here. Too many I's and U's next to E, Q, U, I, L, I, B, R, I, U. There we go, equilibrium. Two conditions have to be met. Summation of the forces equals 0, which, as I mentioned, is just Newton's second law. It's just Newton's second law with A equals 0. Better lighting conditions again. In addition, summation of the torques has to equal 0, which is just I alpha with alpha equals 0. No translational acceleration, no rotational acceleration. For our purposes, this translates into, if you want to just write down equations with numbers in them instead of vector equations, for our purposes, this will be 3 constraints. Sum of the forces in the x equals 0, sum of the forces in the y direction equals 0, sum of the torques in the z direction equals 0. If you take a more advanced course, then actually there's 6 equations here rather than 3. Some of the forces in the x, some of the forces in the y, some of the forces in the z, some of the torques in the x, some of the torques in the y, some of the torques in the z. But we'll stay with problems in a plane where things always just would rotate about the z-axis, except they're not rotating because we assume they're in equilibrium. Illustrate this with a few examples. Looks like I need to turn the page. Oh, how nice, it focused. Okay, so number 3. you've got something like a tailgate on the back of a pickup truck. You've got a hinge over here, and this cable supports the thing and keeps the tailgate from just flopping down like that. Same thing if it was a drawbridge on a castle. So gives the weight of it, how long it is. Since the question says nothing to the contrary, we'll have to assume it's a uniform object, which realistically might not be exactly true, but the center of gravity of a real tailgate is probably within an inch or so of the middle of it, somewhere pretty close. So it asks for three things: the tension in the cable, and also, see, there's a force over here at the hinge also. I mean, think about it. If you were to slide the pin out of that hinge, the whole thing would just sort of collapse like that. So there's a force here that we know nothing about, the magnitude or the direction. There's a force over here that we know lies along the cable, 50 degrees above the horizontal there. So three variables, the tension, and then the X and Y components. So the first step, as I've, let's see, where did I leave off? Guess I'm over here. The first step, as with any problem of this general sort, is a free body diagram. You need a sketch showing what all the forces are, where they act, and free body diagram shows just the object under consideration. So just the tailgate, never mind the rest of the truck. Pivoted over there. I'm going to go with C for cable. T for tension just gets too confusing when you got tau for torque and T for tension, and they look a lot like each other, and let's just not do that. So the force from the cable, 50 degrees. The tension in a flexible cord has to pull, never push, it has to pull right along the cord. Over here, on the other hand, the force from this pin here in this hinge could point in any direction. So what we're going to do is represent it by X and Y components. HX, X component from the hinge, HY, Y component from the hinge, and then no matter which way it points, we're covered. You know, if it points to the left, the X component would just be negative. Any way it goes, we're good. And then the weight of the tailgate itself goes at its center of gravity, which, like I said a minute ago, since we don't have any information to the contrary, we'll just assume it's right in the middle of it. So if the whole tailgate is 80 centimeters long, from the pivot to the center of gravity would be 40 centimeters. And then to the other end where C acts, that's 80. So there's the situation. The first thing I'm going to do is use the second condition of equilibrium, because just looking at the picture, I can see that I'm not going to get anywhere using some of the forces equals zero. Some of the forces in the X direction, that equation would contain two things that I don't know. It would contain HX, and it would also contain C times the cosine of 50 degrees. One equation, two variables, No good. Never going to get an answer out of that. Same problem in the y direction. You've got HY and c times the sine of 50. Again, equation with two variables in it. So between those two equations, there's three unknowns. That's a problem. But if I use torques, notice that two of the three things I don't know pass right through the pivot point. Okay, so when I do R, torque is R cross F. And for each of these two forces, R equals 0. Okay, where R is the radius from the pivot point to where the force acts. And both of these forces act right at the pivot point. So two of my three unknowns get multiplied by 0. That's going to give me an equation with only one variable in it. That I can actually get somewhere with. So that's the kind of thinking that leads me to start out with the second condition. Summation of the torques about the point P, P for pivot, is equal to 0. The way that's read is summation of the torques about point P. Okay, summation of the torques about point P equals 0. Well, normally you wouldn't bother to write it out in quite this much detail because a couple of the terms are just equal to 0, but just to kind of be thorough and explain everything. Just a moment. I'm just going to work my way along the picture and multiply every force there is by the appropriate moment arm. So HY, the y component of the hinge force, its distance from the pivot point is 0. So 0 times HY. Like I said, I wouldn't normally bother to write that down, but since I've got a bunch of beginners watching me, I should probably cover all the details. HX also passes right through the pivot point. So 0 times HX. Next thing I come to, the weight. Now, if this was the only force acting on this tailgate, it would make the thing rotate this way. That's clockwise. So clockwise is negative. It's a minus sign. The force acts, well, it doesn't really matter. You can use centimeters, you can use meters as long as you're consistent about it, but we'll go with 0.4 of a meter. Okay, we've got 200 newtons acting 0.4 of a meter from the pivot. The cable, if that was the only force present, it would make the tailgate turn this way. So that's, right-hand rule. That's a torque in the positive z direction. Or just remember the rule, counterclockwise is positive. Actually, for a simple problem, well, simple is relative, but compared to something three-dimensional, for a problem like this one, you can get away with doing it left-handed, okay? You could, as long as opposite directions get opposite signs, you could say clockwise was positive, and you get the right answer. The 80 centimeters is not perpendicular to the force C. So remember the sine theta factor. R cross F means RF sine of theta. So we've got 0.8 of a meter times the sine of 50 degrees R times F times the sine of the angle in between them. And the total of all those torques has to be 0 if this thing is going to remain at rest. So a couple lines of math. 0.4 times, of course, 0, 0, they just go away. 0.4 times 200 is 80. And 0.8 times the sine of 50 is 0.613, or at least that's what it rounds off to. Add the 80 to both sides, then divide by the 0.613. And the tension in that cable is 131 newtons. That's just one of the 3 answers the question asks for. There's actually more than one way of proceeding from here that would get you HY and HX. But I think the most straightforward way to look at it is now to switch over to using forces rather than torques, okay? My problem before was I had too many unknowns, but one of those unknowns has become known at this point. So some of the forces in the X direction will give me HX, some of the forces in the Y direction will give me HY, and that's how I'm going to wrap up the rest of it. If you're going to work with forces, you know, X forces, Y forces, you need X and Y components of everything. So I'm going to start out by getting the components of this 131 newtons, okay? You've got 131 newtons at 50 degrees from the left-hand side of the x-axis. So I'm going to go over here and draw the little triangle, figure out those. Hypotenuse times cosine gets you the adjacent side. Hypotenuse times sine gets you the opposite side. So the forces that you really have from back over there, I don't know how clearly it shows up from this distance, but the forces you really have are equivalent to, here's the tailgate again. There's HY, there's HX, there's the weight, and the 131 at an angle is equivalent to 100 pulling up and 83.9 pulling to the left, these two forces acting together are in every way equivalent to the force that you've really got. That's kind of what components means, okay? So looking at that, summation of the forces in the x direction is equal to 0. Every place there's a vertical arrow, that's one of the terms in this summation. Well, or no, I'm sorry, x. Every place there's a horizontal arrow. I'll get to vertical in a minute. Horizontally, I've got this arrow here pulling to the right, or pushing to the right. So hx is positive. And I've got this 83.9 acting to the left. That one gets a minus sign. Tough math here. Solve for x, or hx. And then same kind of thing with the y components. Every place there's a vertical arrow on the picture. That's a term in this summation. You've got PHY. Also pulling upward, you've got the 100 here at the other end. And you've got the 200 downward. So in this case, it comes out symmetrical, 100 newtons at each end. If, for example, the center of gravity hadn't been right in the middle, then these two would have been different from each other, but in this case, they're the same. Well, let's see, what else have I got for you here? Maybe I better put it back over here for a moment. Oh, yeah. You got some sort of a platform supported by ropes at each end, like some sort of a platform that somebody's standing on washing the windows on a tall building or something like that, except I made it a box instead of a guy with a squeegee. So realistically, you'd probably have a system of ropes on each end so that you don't have to tip toward the front or the back. But to simplify the question down, let's just imagine a single rope on the left and a single rope on the right. And if this box is sitting there, what does the tension in each of those ropes have to be? Well, the thing that's a little bit different about this one is there isn't something labeled on it that says this is the pivot, okay? For everything that we've encountered so far, there was something like in this example up here, where there's a little dot on the picture somewhere, and I've written on it, this is the hinge or something. There's no hinges on this thing. It's just a board with a rope tied to each end and a box sitting on it. And so how are you supposed to know which point you have to take the torques about? How do you know where the pivot is? Well, as it says up here, you're actually free to choose, okay? Which is convenient. You get to pick something that'll make things as easy as possible instead of being stuck with something that you have to do. But think of it this way. If the rope on the right was to suddenly break, then it would start to pivot about the point on the left, like that. But as long as the rope does not break, you can think of this board as not rotating about point A. By the same token, if the rope on the other end was to break, the board would suddenly begin rotating about point B. But as long as this one doesn't break, you can think of it as not rotating about this point. As long as it's an object at rest remaining at rest, you can think of it as not rotating about any point you pick. It doesn't even have to be a point on the object. You could use this point over, well, I'm off camera here. Go over here then. This point up here, just in the middle of nowhere. If for some reason that seemed convenient, you could take your torques about that point. Because after all, the board is not rotating about that point also. So well, let me go ahead and get the diagram drawn, and then I'll talk about what's the smart choice. In principle, any choice is correct, but some choices will make life easier for you than others. But first of all, here's the free body diagram. So there's a force at point A that I'll call force A. Yeah, A is the name of the point, and FA is the force that acts at that point. And over here, B is the name of that point, and FB is the name of the force that pulls on that point. In addition, there's the weight of the board itself. It says it weighs 150 newtons. Here again, the question gives us no information to the contrary, so we'll assume it's a uniform object. And so the weight is right in the center. And I'll label all the distances in a moment here, because we need them also. The box is over here, and it presses down on the board with 150 newtons. Okay, so as I said, in principle, you could take torques about that point if you wanted to, but you would probably regret that somewhere around your third page. Well, it wouldn't be quite that bad, but the smart choice is to use one of the ends because, well, nobody actually tries to use that point, but one thing I see people do every now and then is try to take torques around the center. The problem is that gives you an equation with two variables in it. You're going to, see this thing is 3 meters long, so you're going to have one term in the equation that's 1.5 meters times FA, and you're going to have another term in the equation that's 1.5 meters times FB. And you'll eventually get to the right answer that way. You'll have to get another equation that involves the same two variables, and then you solve the system of equations, and that works. But life is a little nicer if you write an equation that only has one variable in it in the first place. So pick a point that has as many of the unknowns as possible passing through it, like this one back here. Yeah, it said this is the hinge, and that seemed like enough of a reason to take my torques about that point there. But even if it hadn't been a hinge, that's the point to go with, because see, two of the three unknowns get multiplied by 0. That gives you the simplest equation. So I want to do the same kind of thing over here and pick a point to call my pivot that has one of the unknowns passing through it. so that I get an equation with only one variable. Could use point A, could use point B, makes absolutely no difference. It's going to be exactly the same amount of pain and suffering with either one of those choices. Looks like when I wrote this out, I went with point B. Like I said, A would have been just as good. So labeling all the distances from point B, that's going to be my pivot. Summation of the torques about point B is equal to 0. This force, the weight, is right exactly in the middle. So half of 3 meters is 1.5. Over to where this is. Well, on the question, it's labeled 1.2 meters, which would be the distance you'd use if you're considering A to be the pivot. But I was just in the mood to use point B. So 3 minus 1.2 gives me 1.8. And then force A is the full 3 meters away. Working my way along, maybe I'll start at the pivot point here. Force B passes right through the pivot, so it gets multiplied by 0. Next, the 200 and the 150, they're trying to make the thing turn counterclockwise. They'll get plus signs. Force A creates a torque that's trying to turn it clockwise, so that one will get a minus. Remember, when you're dealing with torques, counterclockwise versus clockwise is what determines plus or minus. It's not about up versus down. That's forces. So 0 times force B plus 1.5 meters (1.5 times 200). And then the 150 acts 1.8 meters from the pivot. Our unknown force is 3 meters from the pivot. Torque equals force times moment arm. In each case, the distances that have been labeled are perpendicular to the force. So if you wanted to fill in the sine theta factor, it's just the sine of 90 degrees anyhow, which is equal to 1. 1.5 times 200 is 300. 1.8 times 150 is 270. $300 plus 270 is 570, and divide by 3. There's one of our 2 answers. you can still see the diagram. So now, well, like I said at this point in the previous question, there's more than one way to go. One way to finish it off is you could write another torque equation, okay? The one that I just did, I took my torques about point B, and that gave me an equation that force A appears in. The other, what you could do now is you could take torques about point A, that would give you an equation that force B appears in. And that's a perfectly good way to do the second half of the problem. Myself, it seems like there's a little bit less to do, just personal opinion, if I switch over to using forces instead of torques. So I'm going to say sum of the forces in the y direction equals 0. So now, plus versus minus is a matter of up versus down, rather than clockwise versus counterclockwise. And now you don't multiply by any moment arms. For forces, it doesn't matter where the force acts. Just which way does it pull is the only thing that matters for this kind of thing. So you look at the diagram. You got two forces up, you've got two forces down. So FA and FB, they'll be positive, and these two guys are negative. Doesn't matter if the force acts at the pivot point. You're not multiplying it by a moment arm. This is forces, not torques. Well, we now know that force A is 190 newtons. Figured that out back over here. So, well, that minus that minus that, you know, a couple lines of pretty obvious algebra. Force B comes out 160 newtons. It's often a good idea when you get to the answer to sit back and ask yourself whether it makes sense. Well, the force that's closer to the box, you know, the end that's closer to it bears a greater share of its weight. So 190 for the closer rope, 160 for the farther one. Yeah, that makes sense. If it's coming out the other way around, you might want to go back and try and figure out where you mixed something up. One more example, and that'll polish off section 8. Well, except of course for doing all the homework. In my humble opinion, doing the homework is probably the most important part of the course, because that's where you get to practice doing this stuff yourself. Whether or not you do the homework probably matters more than whether or not you come to class. Okay, I'm not sure who stores their chairs in a position like this, but just as sort of a hypothetical thing you could do if you felt like it. You've got a table over here, a short distance from the wall, and you've sat a chair with the front legs on the table, the back legs kind of hanging in empty space, and the back of the chair leaning against the wall. The center of gravity is this point down. There's nothing that says the center of gravity has to lie within the object itself. Like, you know, if you go to Dunkin' Donuts and buy a donut or a bagel, the center of gravity is right in the middle of the hole, okay? So the center of gravity is a short distance below the seat, kind of toward the back. right there. And there's all sorts of dimensions labeled, some of which are useful and some of which are not. What I was sort of thinking is at this point, diminishing returns have set in as far as you just sitting there passively watching me do things, like I probably said at the beginning of the course. After a little while, watching somebody else swim is not helpful for you learning to swim. You need to get in the water and splash around and get a feel for it yourself. So I usually give the class about 15 or 20 minutes at this point to work on it. Well, actually, what I usually do is I give them a few minutes and then I draw the free body diagram, because anybody who hasn't gotten that far after 3 or 4 minutes probably needs some help. And then I give them like another 10 minutes to try and actually solve the problem. So let's try and simulate this at home, everybody. Pause it here, go as far as you can. I'll draw the free body diagram and then give you some more time after that. And I'll stop talking now. Okay, just the free body diagram of the chair. And some more time after that. And by the way, if you need help getting through this thing the first time, my advice is after you've watched me explain the parts you couldn't do, is pause the recording again, see if you can do it after I've showed you the parts that you weren't able to do. If you can't do this one, well, let's put the positive spin on this. If you can do this one, you're probably in good shape. So work on this until you can do it yourself without just sitting there watching me do it. Just pause the video with the question in front of you, and if you can get all the way through to the right answers, just off of a blank sheet of paper with your formula sheet and a calculator there, that's what you need to do at this point. So here's the chair, maybe a little bigger. Center of gravity is located about there. That's where the object's weight can be thought of as acting. 50 newtons. The top of the chair leans against the wall. Since it's part A of the question that asks for that force, I thought I'd call it A. Now, the question says the wall is frictionless. Probably not entirely realistic, but under the right circumstances, friction might be pretty small. Anyhow, going with what the question says, without questioning too much whether something would really do that, if there is no friction force, then there's no y component up here, okay? A is the normal force acting at this point. So normal to the wall, you have this force that I called A. And there is no friction force to be in the y direction. Over here on the front leg, on the other hand, you have both, well, part B says the x component of the force on the front legs. This would be the total on both legs. So part B asks for that. Part C asks for that. I'm going to refer to this point as point P because I'm going to want to have a name for it. And as far as what are, well, you know, I don't want to say too much right now because then I'd start giving away how to do it. But there's all the forces. You know the one, you've got three unknowns. So based on how I went over the two previous problems, see if you can finish it off from there. So pause the recording here. And now I imagine you've unpaused it and are eagerly waiting to see how I do this. By the way, the answers are, because I only put the one of them underneath the question. For A, it's 18 2/3 newtons. B is also 18 2/3 newtons. And C is 50 newtons. And if you figured that all out on your own, yeah, this is pretty much the end of section 8. But if you need to hear me talk you through it, I'm going to do the summation of the torques about point P. For the reason, I'm starting with that for the reasons I explained when I was doing those other problems. 2 of my 3 unknowns pass through point P. So considering this point to be the pivot will give me a simpler equation than most other choices. Both B and C will get multiplied by 0. If this is going to be my pivot, I need to know how far each of these other forces acts from there. There's the line of action for point A. The moment arm means the distance from the pivot to the line of action. Well, that's one of the many numbers that's labeled on the diagram. The pivot point is 75 centimeters from this line. So this is going to be A times, if you do it in centimeters, 75. If you do it in meters, 0.75. So, you know, when there's a lot of clutter like this, it's not a bad idea to draw a separate little picture for what's going on with each force. So pivot point is down here somewhere, and force A is over here somewhere. And for figuring out the torque from point A, this is pretty much all that matters. A goes along there. This is 0.75. Well, I guess I was going to go with centimeters. That's fine. 75 centimeters. So that one's a negative torque. Okay. That's trying to rotate the chair this way around point P. So minus 75 centimeters. Torque equals force times the moment arm. A times A's distance from the pivot. And then there's the weight. So you've got the pivot point over here. And you've got 50 newtons. And 50 newtons acts along that line. The distance from the pivot to that line of action would be that far. And if you pick that out of the, you know, from there to there is what we're talking about. That's 28 centimeters. So This force is trying to cause counterclockwise rotation around that point. So it gets a plus sign. "28 centimeters times 50. And again, if you work in meters, all that does is divide the whole equation through by 100, which is going to have the same solution. So it doesn't matter. 0.28 meters, 28 centimeters. Pick your favorite. As for B and C, they both act right at the pivot, so neither one of them produces any torque. Summation of the torque is about point P equals 0. Where this is the torque from that one, this is the torque from that one, and so on. So we've got, if I add the 75A to both sides, (28 times 50 is 1,400. Add the 75A to both sides, and then divide. So that's the force from the wall pushing against the upper end of the chair. Now, kind of the same pattern as the two previous examples. To get my other two unknown forces, I'm going to switch over to using sum of the forces equals 0. Summation of the forces in the x direction is 0. Otherwise, the chair would start to accelerate toward the right or the left. Every place there's a horizontal arrow on the picture, that's one of the forces in that summation. Well, there's only two horizontal forces, A and B. So A to the right, B to the left. And in order to maintain translational equilibrium, A and B have to be the same size. Otherwise, the chair would begin moving toward the right or the left. Same sort of thing with the y components. Every place there's a vertical arrow on the picture. Well, there's only two vertical arrows. The 50 newtons pulling down and force C pushing up. So you've got C minus 50 equals 0. Extremely simple. Well, parts B and C are extreme. A, not so much, but parts B and C are extremely simple once you see how to look at it. But of course, how to look at stuff is kind of the main point of the whole course. People like to approach a physics course from, it's like, well, I'm going to throw numbers at equations. What equation should I throw numbers at right now? And the problem is you end up throwing the wrong numbers at the wrong equations, if you don't see the right way of looking at things, which is why I started out with those conceptual questions about the, you know, the tailgate on the SUV and all of that sort of thing. So that wraps up section 8. And then I'll stop the recording.